So welcome back, and our second speaker of this afternoon is Balt van Rees, talking about estimate for modular bootstrap.
All right, thanks for having me. Thanks for organizing this seminar series. That's the first time I'm attending, and I'm asked to speak immediately. So I'll talk about some relatively simple question, I think, simple to formulate, and the progress we made in the end was based on very simple mathematics. So I hope you'll all be following it. So this is also a warning sign that if there's something you don't understand, it's me, right? So you should be able to understand all of this completely.
Or maybe it's us and you are over.
Please ask. Oh, sorry?
Sorry.
No, it's definitely no. This should all be understandable. So you should ask questions if something is, anything is unclear. So I'm going to be looking at 2D CFTs. I don't know, they're local, they're unitary. Should I say anything else? Their central charge should be bigger than 1. And should have a unique normalizable vacuum. So in the end, I'm just going to look at the partition function that I already wrote here, the torus partition function. The one thing that is non-standard here is that I am going to look at what I'm going to call non-rational CFTs, which means they have a twist gap. So you will have your vacuum, which will be a unique ground state, but I'm going to say for every state after that, or every local operator that, I'm going to say that the twist delta minus j is going to be bounded from below. So it's all, for any state, it's going to be greater than some number that I'm going to call 2 times t gap, and t gap is some number that is strictly positive. So of Virasoro primaries, obviously you have the Virasoro descendants of the identity, but those have twist 0. But after that, so for Virasoro primaries, I'm going to assume this twist gap. So this is for all delta j. We'll see what this means for the modular invariant partition function. So then you have your Hilbert space on the cylinder. You take the trace with these operators, Hamiltonian translation. You have your fugacities, beta left and beta right, and that defines your partition function, which is of course going to be modular invariant. So what should I say? I mean, let me first say that this is some spectral density here that you have. So rho, you can rewrite this as in terms of some integrals over h and h bar, where rho is some density, and then h and h bar are basically, so what should I say? H is delta minus j over 2, h bar is delta plus j over 2, and delta minus c over 24 is the eigenvalue of capital H, and j is the eigenvalue of capital P, the operator. I should have, so in unitary theories, h and h bar are both non-negative, and rho, you should think of it as some kind of spectral density, right? Sum over h bar, delta h minus sum over hk, delta h bar minus h bar. So I'm not necessarily going to assume a discrete spectrum, but if the theory has a discrete spectrum, then the spectral density looks like this. And then, of course, you realize, well, you still have your Virasoro symmetry. So all these operators, if I have a particular operator, then I should also have all of its Virasoro descendants. So you get the decomposition of this Hilbert space in representations of Virasoro. So it's maybe better to just separate out the Virasoro primaries, ZP, and then take into account all the descendants by just dividing this by the theta function. Let me see what I had for notation. I pi beta left over 2 pi. Where eta is your familiar eta function. Product n 1 minus q2. Right. So this is a path integral over torus, so it's going to be modular invariant, and this ZP gadget, because the eta function also is a modular covariant, this ZP gadget is going to be modular covariant. So that's the thing we're going to look at. It's the spectral, it's the partition function for Virasoro primaries. So it'll be also be written as a spectral density. H, the H bar, but now the spectral density of Virasoro primaries. So it's going to look a bit like this, but I'm not going to write a superscript on it because this is the thing I'll be working with in the whole talk. So it will be something like this. E to the minus beta left, H minus C over 24 minus 1 over 24. So that's what we're going to call A. E to the minus beta right. 4 minus A equals C minus 1 over 24. So now this guy will be the spectral density of Virasoro primaries. And of course, let me separate out the guy corresponding to the unique vacuum. So that'll just give me the one with H equals H bar equals 0. Right. Yes. And then, of course, there's L minus 1 on the vacuum is 0, so you need to, with this eta function for the Virasoro, for the vacuum, I factored out a bit too much, and that you compensate with this extra little bit. And then modular invariance. So this is my partition function, and modular covariance of this guy, because the eta function says that ZP, eta left, eta right equals ZP, eta left plus 2 pi I minus 2 pi I equals 4 pi squared. Eta left, eta right, Z 4 pi squared over beta left. And the whole setup of the problem is this. These two equations define everything I want to talk about. So you have some spectral density here, some rho HH bar, which you can think of like this, a bunch of delta functions with coefficient 1. So rho is a positive spectral density. Yep. Sorry? ZP, yeah, it's all P's, thanks. Yeah. So this defines the spectral density, defines for me some function, which is basically the Laplace transform spectral density. Then there's one funny term coming from the vacuum. And apart from that, these integrals, they start at this value, funky value T gap. They go up to infinity. And it's modular covariant. So this is it. And the question of the so-called modular bootstrap, what we as physicists call the modular bootstrap now, is basically, if you have these two equations, 1 and 2, what are the consequences? So the question is, what are the consequences of 1 and 2, which are written in terms of the partition function? What are they for the spectral density? Can we derive some general properties of this spectral density? Can we maybe derive properties for specific theories, put in a specific value of the central charge, and get some specific consequences? Can we say, what kind of general properties can we derive? And this should be, I think, completely understandable for everyone. This setup is very, very concrete. And of course, they're big. I mean, nowadays,
Beta left and beta right are analytic, are complex for I.
Right, so you can ask, okay, where should I take beta left and beta right to be? And we're going to say that this integral, yeah, you're right, this integral is defined for beta left. We're supposing that rho is such that this makes sense in some formal way. You can call it a Riemann-Stieltjes integral, but this makes sense when beta left and beta right are both have positive real part, or both real and positive initially. But of course, if you add an imaginary part, it's going to be fine too. So, so this I actually have it in the notes. This should work for beta left and beta right in the right half. So here you have an analytic function defined in terms of the spectral density, analytic in a polydisk essentially, and what are the consequences? And it's somehow modular covariance. So what are the consequences for the spectral density? I mean, so of course you can ask a ton of questions, and you can relate this to sphere packing and quantum gravity, large central charge, and so on and so on. Today, I'm going to be looking only at the large spin limit, which is sort of the large h bar limit, which is related to beta right, 0, beta left fixed. That's the only limit I'm going to look at. And even so, I mean, I think it's an interesting question. I mean, I can give you some motivations. So first of all, well, these non-rational CFTs are a bit obscure, a bit. We don't really know of many such examples. So it would just be nice to see some general, to do some general properties of these non-rational CFTs. That'll be universally valid as soon as you have such a partition function, which is supposed to be always the case. And then in fact, we don't really know for sure that these non-rational theories even exist. So you can ask about, well, this is obviously not going to happen, but you could ask, is this even consistent, this setup? Or is there going to be some way in which this setup is problematic? That would be really cool. So you can show that these non-rational theories do not exist. Nobody believes that they do not exist. But in principle, since we don't have an existence proof of these non-rational theories, it would be, we should see that there's no contradiction.
What you mean some kind of non-perturbative beside the constructions that involve coupling minimal models?
Yeah, exactly. I mean, these theories are also supposed to be chaotic, and there should be some connection to random matrices and chaos. I'm not going to talk about it much, but you can ask at least, well, one thing you can ask is in which sense is there a connection to chaos, right? You need, if you want some random matrix, you have to do some statistics. So there have to be at least infinitely many terms in this spectral density of your zero primaries, otherwise you cannot really do meaningful statistics. So can we see some of that? And then there's a connection between this and the things Sriklip, Shashin, and I are using, and the lightcone bootstrap, which interests me for. So this is also a warm-up for the so-called lightcone bootstrap. If you don't know what it is, don't worry about it. But that in turn has to do with the analytic properties of scattering amplitudes. In more than two space-time dimensions. So I think I'd like to understand this lightcone bootstrap myself a lot better, and you should ask me afterwards if you want to know what I want to do there. All right. So this is the setup. So you can play all kinds of game. First of all, I should mention, of course, that equation 1 there out of equation 1 and 2 is very easy to solve. And you've all obviously seen it already. 1 just means that h bar minus h should be an integer, and for all, so rho should have support only when h bar minus h is an integer. And in fact, that completely solves one. So one we're completely done. So we can also write sum over all integers. The spectral density, we can just write it as a sum over the integers. And then there's some factor 2 from some annoying Jacobian. But then you want to do something like this. So h bar minus h is an integer. So now you have the delta functions which supported the integers. Rho j is then some spectral density. Rho of spin j operators in the CFT. Rho j delta is sum over k delta. Right, and by the state operator correspondence, these are just the operators of spin j that are in the CFT. And delta are the scaling dimensions. And delta is always bigger than j, so plus t gap, so h is always plus 2 t gap, so h is still above t gap. All right. So that solves one. One is done. And two, well, I wrote it as two is sort of the connection between the first thing I wrote and the second thing I wrote, right? That's the one is not solved, so that's improvement. So what about two? Two, we don't know how to solve it or what all of the consequences are of it. Two is much more difficult. One thing so the only thing I'm going to look at, like I said, is just the beta right to 0 limit. So let's send beta right to 0 on both sides and see what happens. So here, beta right, it's easiest to do it here. Beta right to 0 here means that the second argument goes to infinity, plus infinity. And so it means that these terms are all very much suppressed every time you see e to the minus something. And the leading term is going to be this one with h equals 0. So it's e to the a beta right. That's going to dominate everything else because these h's are above t gap. So this is where my twist gap is important. So this is the right-hand side that's going to dominate, right? So we get an exponentially, so let me write first the right-hand side. As beta right goes to 0, I get just that leading term transformed with the 4 pi squared over beta left and so on. So I can write it as the vacuum in the cross channel beta left, vacuum in the cross channel beta right, where my vacuum term in the cross channel is just that factor transformed. Beta is e to the a beta right, no, transformed a 4 pi squared over beta right. Then there's the prefactor, square root of 2 pi over beta right. And if I want to be ambitious, I include also the first subleading term. So that's what happens in the dual side. And it's this, I mean, I really wrote a bit more than I needed to. So this VC beta right, I only care about the leading term. But since I keep beta left fixed, right, I have this thing which is completely fine. So that's why I write twice. So this VC plays kind of a dual role. For beta right, it's only the leading term that matters. But for beta left, which is arbitrary, I need to fold.
In your subleading term, you should have 4 pi over beta.
Yeah, thank you. Yes, I'll start. So I get some exponential growth, and I want to say, well, what's going to reproduce that exponential growth? Well, it's definitely not this term. It's definitely not the vacuum term itself. That one, right, as beta right goes to 0, it's just completely finite. So it must come, beta right goes to 0. So basically here, all the operators with a given h bar, they get basically all the same weight. So you're basically counting all these operators with large h bar. So it must come from the large h bar part in this integral. So that already shows you that there must be infinitely many, otherwise you're never going to get this to be able to get some exponential divergence. And the question is, of course, how infinitely many do we really need? So let me just write. So it's not going to come from the vacuum part. So all I can just write for the left-hand side just the part that is actually going to reproduce this exponential divergence, which is basically the same thing as I wrote before. It's just that left, the right, right. So now you can ask, okay, what does rho need to do? It needs to grow very fast. You need a lot of operators to get this exponential divergence. But what does it exactly need to do, right? How precise can we be about the behavior of this rho? This is the spectral density. It's a density of operators. We're asking about large H bar, but can you say something like without big O symbols, small O symbols? Can you say something about H bar equals 10, H bar equals 12, H bar equals, right, 100? At what point can we say something? Can we make precise predictions rather than vague estimates? So that is the aim, but for the moment, let's just try to do something very naive and say, okay, can I write this as some kind of spectral density? Right? Can I just write this as the integral dh bar, rho of h bar, e to the minus beta, right? H bar minus beta, for some rho naught of h bar. That'll give me some idea of what I need, right? Because then we'll just look at the large h bar limit of this to see roughly what we need this rho of h bar to do. And of course, this is just the Laplace transform, so I can just take the inverse Laplace transform. Rho naught of h bar is just the inverse Laplace transform of this VC. So right over 2 pi I for some gamma greater than 0. Right, you do some inverse Laplace transform in the right half plane. We had analyticity there, so everything is kosher. H bar minus A. And this you can do. This is a simple integral, and it turns out. I mean, I'm going to write it in detail because for beta right, fine, we need just the leading term, right? Like I said, so I just need the asymptotics and I'm going to write it, but for beta left, we kind of need the full thing. So let me just write the full thing, and the full thing is 2 inside the square root, 2 over h minus a, hyperbolic cosine, 4 pi a times h minus a minus hyperbolic cosine of, so it gets a bit dense, a minus 1. So you can kind of see where, right? This hyperbolic cosine is for the leading term, and this hyperbolic cosine is for this. So this is, and otherwise it is 0. So this is if h is greater than a. I'm working with h bars, so I should have bars on everything. And if h bar is less than a, then it's. So that should be, that's roughly that would be a spectral density in the single variable case that would reproduce this. So you can see that this rho of h bar, as h bar goes to infinity, well, you see what the leading behavior is. It's just the exponential from the cosine. So it's the square root of 1 over, I want to write it like this, 1 over the square root of 2 h bar. The shift with a I can ignore, and then it's e to the 4 pi. That's the leading behavior. Right, so we don't need quite exponentially many operators, but we need exponential of the square root. And with my collaborators, I was always saying this is exponential, and then they were like, this is not exponential h bar. So let's say a bit less than exponential is what we need. That's seemingly what we need the spectral density to grow like.
Which is a typical theta series growth rate.
It's I mean, this is all, yeah, it's Cardy, it's whatever, yes. So it's all very familiar stuff. And I don't know if I want to say more. This cosine this hyperbolic cosine, you can sketch what rho 0 of h bar looks like as a certain function of h bar. And it starts at A, and then it grows, and then there's this exponential growth here. And that's the part we're looking at. This dip is sometimes there, it depends a bit on the central charge. Sometimes it's just one time. Okay, so we seem to need this nearly exponential growth in the number of operators at large h bar. So now you can write a prediction. You can say, well, right, I have this beta right, so that needs the exponential growth to reproduce the exponential growth here. I need this square root h bar part. And then for the beta left, I just also take the inverse Laplace transform. So my prediction will be that rho of h bar will be in some sense, as h bar goes to infinity, it'll behave like e to the 4 pi square root a h bar over the square roots of 2 h bar. And then the same thing, rho 0 h to reproduce the beta left dependence. Right? So in which sense can this be true? This is Cardy's formula in the lightcone limit, that there's not a real good paper to cite because it was Tom Hartman in some unpublished work who sort of first analyzed this. This is sort of the obvious single variable version. If you Cardy basically sent both beta right, he looked at the diagonal, beta left and beta right going to 0 both at the same time. And now we're just sending beta right to 0, but it's all exactly Cardy's form. But then, right, in which sense can this be true? I wrote a funky arrow. I mean, in the literature, you can see this and you can see this. Cardy had an equal sign. That's kind of, and you can see all kinds of estimates. We saw some this morning in the first talk, which was great, but there was this, and I forgot what Boris wrote. Boris, maybe he did this. I don't know, but it was exactly the same type of equation. Because in which sense can this be true? Rho is this bunch of delta functions generally. So even if you look at this rho j, maybe it's better to write it in terms of rho j. I can just write the equivalent term because h bar and j, they become basically equal at fixed h. So the same statement, let me write it here. It's just that rho j of j plus 2h is supposed to be, as j goes to infinity, e to the 4 pi square root aj square root 2j out of h. Right, and now it's maybe even clearer that this cannot be normally completely correct because this rho j of delta is some bunch of delta functions. It's a distribution, and here we have some smooth function. So the real question that we're after is to write some equalities, some things that are rigorously true. And what people in the literature correctly say is what you have to do is some averaging. In some average sense, this will be equal to that, which is fine. But then you should ask, well, what kind of averaging, right? Do I have to average over spins, or does every single spin behave in this particular way? And do I have to average over h? If I have to average over h, with what kind of averaging function? Smooth, a block function, clearly not a delta function, right? That would be too much. This cannot be a pointwise limit in any sense, because this rho, we believe it to be some distribution like this. So, but maybe if I integrate with some smooth function, then this will be okay. And of course, if you want to be ambitious, you say, well, I average over some window of h's at some spin. Maybe I can shrink my averaging function as a function of spin. So I make the averaging function smaller and smaller as I increase my spin. And maybe I can still say something. So those are the type of questions that you can naturally ask now. And those are the type of questions that we try to answer. Yes.
Is it meaningful to say that this limit holds in some distributional sense, or
Yeah, but in which case, right? A compactly supported smooth test function, a block function, that's exactly in which case does it? Okay, thanks. Yeah. So actually, I mean, the upshot will be that this holds spin by spin, at least in like when you integrate it against compactly supported smooth test functions, infinitely. We have some stronger results, and I'll mention it at the end. And but first, I before we get to our result, partially because our result is a bit too yeah, it's nice, but I want to give a little bit of context also, because what people usually do here is also interesting. If you have these kind of sort of you have an expression of this form where you have the asymptotics of the Laplace transform, and you want to sort of undo the Laplace transform. So the usual approaches are based on what's called Tauberian theorems. Which are very nice. There's some textbooks written on them, and this is how we started initially, how many of these rigorous results actually have been derived so far, almost all of them. And Tauberian theorems, I mean, the simplest example is of course following. So you do something like this, you sum over all k, you get this. But Tauberian theorems tell you something else. It says that if you sum over all k with some random coefficients, and then you know that as x goes to 1, this function that you get also behaves like 1 over 1 minus x, then you know something about the coefficients. And what you know about the coefficients is that, under some assumptions that I'll get to, is that these coefficients are asymptotically looking, they look like 1. In the sense, and the precise statement is that so this is as lambda goes to infinity is the sum of 1, which is just so when I write this now, right, you see there's a precise limit to be defined. You can say the limit of the ratio of the left and the right hand side is 1. So that's a Tauberian theorem, and this is under conditions that the CK are bounded from below. For me, it suffices to say that they're positive because my spectral density rho is positive. So here you see even something simple as this, you see that you need an average, you need to average over k, right? And this is clear. I can give you, there are examples where the limit of the ck does not exist. So for example, 2 sum over k x squared, that's just 2 over 1 minus x squared, which is 2 over, which also in this limit goes to 1 over 1 minus x. And here the coefficients are 2, 0, 2, 0, 2, 0, and therefore, right, the limit of the coefficients individually does not exist. So it's clear that this, on average they're 1, but you cannot just remove this sum and say that these coefficients, the limit of these coefficients is 1.
X2k.
X2k, thank you. Right, so these Tauberian theorems, they're useful to some extent. They give you some initial ideas. And for us, we looked at the literature of Tauberian theorems. And I can write something quickly here. I'm not going to need this. So there is, there's some, one of the problems with this Tauberian business is that many of the, there's a good textbook, but it's in Russian. And but nowadays, I threw it into DeepL or one of these learning things, and it worked very well. So you can
For the entire
share.
book?
Sorry,
For the entire book?
no, a couple of screenshots, I think, but it made sense of it. It was nice. So there's Ingham's Tauberian theorem, which is actually, you can just find it in the literature, which basically does this kind of game for our case. So you see, this is a power law divergence as x goes to 1, and you can generalize this to arbitrary powers. Here we have some exponential divergence, so things are a little bit different, but not very much. And so Ingham's Tauberian theorem tells you that's, see what you already get the same type of structure, right? You sum over all spins up to some large spin, and then of course we still have the integral over h, rho of rho j of j plus 2h into the minus beta left, h minus a, as lambda goes to infinity. Proper limit here is yeah, it's whatever you're supposed to get, right? So it's the integral up to lambda square root of j. So I mean, this is for large lambda, this is just an integral, and you can do it, but I'm too lazy to do it. And for beta left, you get what you expect. So you see what Ingham does for us. He sort of, this Tauberian theorem allows us to write the h bar integral, right? Undo it for the sum over j's with an e to the minus. There used to be an e to the minus beta right here, j minus a, roughly speaking. And that we translated to a truncated sum. So instead of having this exponential factor, you now have the truncated sum. It's the same as here. You have the x to the k, and you translate it into a truncated sum. So that's what Ingham buys us. And when is this true? Well, initially in the literature, we were a bit confused, I think, maybe as a community, because we were like, okay, these coefficients have to be positive. So we look at, these are now our coefficients, and they're positive when beta left is positive. I mean, beta left equals 0 does not make sense, but you need beta left to be on the real axis, and otherwise you don't have a proper theorem because these coefficients are not necessarily positive. And so that poses a problem because, of course, we still have this beta left dependence, and we want to get rid of it. We want to write something in terms of the spectral density, not its sort of half Laplace transform. So that was a bit annoying. And here you see a beta left, and we want an H, not a beta left. So initially we were like, okay, then as physicists, you can do things non-rigorously and still get away with it. Your paper can still get published. So you can try to expand around large beta left or things like that. But that's, of course, right, not allowed. You have a pointwise limit. You cannot just commute that with an expansion around beta left equals plus infinity. But in fact, I mean, we don't need to be so, right? So if you accept the boundedness from below claim, you can see that if you just insert phases, you're not going to make this behave in a very crazy way, because this spectral density is positive. So actually, it's totally fine to say that this works pointwise for real beta left positive. And that's totally fine. You can also apply, as I initially did, to something called Vitali's theorem, which says, look, this is an analytic function. It converges. It's bounded everywhere in the right half plane uniformly in lambda, which you can kind of show. Also, it's bounded on compact subsets in beta left or in strips even. And so if you have a family of analytic functions, and it converges on some reasonably big subset, then it converges everywhere or it blows up. But if you forbid it from blowing up, then it must converge everywhere. And so this is single variable complex analysis is very simple. it's a consequence of Montel's theorem. So either way, right, you have now this thing everywhere in the right half plane, which is great because you can almost take an inverse Laplace transform. But of course, you cannot quite do an inverse Laplace transform, and this is where your test functions come in. So one thing you can do is you can say, well, I know something now about this thing, rho j plus 2h, integrated against some test function of h, which falls off because then I can essentially use the dominated convergence theorem. Sorry, with the sum still inserted. Sum j to the. So this was the first thing the first new result we got, at least for physicists, it's new. How do you see that you can use dominated convergence? So phi of h is some kind of smooth test function. I always draw a dump function, but it's let's make it compactly supported. So it's let's make it C infinite and compactly supported. So then you're very safe. You can release some of this, but you cannot make it a block function for reasons that we'll see in a second. So if you probe the spectral density in this precise averaged way, I'm going to write something that actually makes sense as a limit. So you see, we average over J in some sense, and we average over H over twists with this compactly supported smooth test function. And you see probably, at least some of you will see what's happening, right? This I can just write as a Fourier. So I can write, I have one integral over h bar, and I split the other one as an integral over h, and then I insert the delta function. So let me just write everything. d beta left over 2 pi I, gamma minus I infinity, gamma plus I infinity. So this beta left is going to be, integral is going to give me a delta function in h and h tilde. So then I have the h from j to lambda. So I think that the equality sign is kind of correct, maybe up to a factor 2. Right, because you can just do the beta left integral and then you get the delta function, and h is equal to h tilde and back where it's left. But now you see what this is. This is basically some kind of Fourier transform of, right, for beta left somewhere in having an imaginary part. So it's a Fourier transform of phi h e to the h gamma minus a. Which, if phi is C infinite and compactly supported, then the multiplication with this factor does not matter, because it's still C infinite and compactly supported. And Fourier transforms of smooth functions, they fall off very fast. So this is bounded in modulus by 1 over 1 plus the imaginary part of beta. So some number that depends on the real part of beta. That I don't care about because I'm only integrating on the imaginary part to some arbitrary power, where n is an arbitrary. C can also depend on this. So it falls off faster than any power, which is way faster than I need, because I'm now going to say, well, let me take the large lambda limit. The large lambda limit of this guy, which is now what sits here, I know it pointwise. So if I would just integrate it, then it would not be allowed to commute the limit in the integral. But now I have some smoothly falling test function that takes care of what happens at large imaginary beta. So since this falls off very fast, I can just use dominated convergence and apply the limit pointwise here to this point. And that's the only that is all I need, because now I can say that the large J limit of this is exactly what you expect. So it is some j2 lambda e to the 4th by square root aj over 2j in the square roots. And then I have this dh rho naught h 5h from a to infinity. And that's what I get. So in this way, if I average in this particular way rho j, right, I get, sorry, this is the limit, of course, as lambda goes to infinity. I get something I understand. So this is already something that was long suspected but never really proven, which means that it says that, look, if you average in this particular way, you're going to get your nearly exponential divergence. So I can plot this rho, which we expect generally to be a sum of delta functions. I can just plot it. H and J or H bar, which synthetically is the same thing. I have my vacuum, which is J equals H equals 0. So that's one state. This is my unique vacuum. Then by hypothesis, I have this T gap. And I have J equals 0. So I have a bunch of operators and they all lie above T gap. Then I have spin 1. I have some other operators, spin 2. I have some others. And then for very, very large spin, we now know that we need to reproduce this exponential divergence. So or nearly exponential. So you expect, right, this is for any row above A. So A is somewhere here. For any row here, we need a spectrum that becomes nearly dense. Right, so we get something that if you sum all these operators here, then you get some dense. So after summing, it becomes some dense spectrum for all h greater than. Because otherwise you will never, right? You can make this guy compactly supported, but on an arbitrarily small interval, even like microscopically small, but not varying with j. And then you still need to get this divergence, right? So in every interval, there will be at least one operator at a certain point. And that's the definition of that.
If I was doing the rational CFT case, I think everything would apply. Just A would be 0. No, it would be 0 in your case.
No, but you have more complicated characters, and then of course you can obey crossing with finitely many.
Yeah, but if I want your gapped condition, I guess I have to have C equal 1. If I'm rational, isn't it? If I had more current. If I had C equal 2, I would have ungapped. Sorry.
I think there's no, but I don't even know okay, maybe for the integer spins, there's something special, but yeah, the problem is, of course, that the right-hand side is not the vacuum anymore. It's not this VCBR, VC, right? This is not, this guy is not the leading term on the right-hand side. So that changes everything. Because this is the vacuum, right? We only have this simple form because we have no other operators of twist 0. And the moment you have more, you get a completely different right-hand side. I don't know what to say. And in the end, of course, yeah, you know that you can obey this thing with finitely many characters of your extended function. But yeah, I don't know. Maybe there's something equivalent you can say if you decompose your extended algebra into Virasoro characters. You can maybe say something. So what happens is, of course, I mean, yeah, no, there of course something else happens because things become integer spaced. And
this is why I was asking, because then it would never get dense, right?
No, and here we show
growing, it's still get.
Yeah, here we show that this integer spacing at some point has to fill, at least if you sum over all spins. So the question is, right, is integer spacing even possible? Well, at this stage, actually, you could have something like integer spaced at some spin, and at the next spin, you have integer space with a small offset. You have again integer space with some offset, and in the end that adds up to something dense. That would be one possibility.
Okay, so
That is still a possibility. You can also, so that's one question, right? So and then of course it doesn't even have to be so nice for every spin. Maybe this is the case for some spins, and then you skip 10 spins where there's nothing, and then you can have, then you fill out the rest of it, right? So one of the natural questions with this result is what happens for individual large spins? That's the next answer, right? Is this, if you sum over all spins, some spins can be an exception. Can individual spins misbehave and do something completely different, or are all spins going to be following this kind of trend? And another question that you could ask if you want to improve this result is, what about shrinking windows, which are already set in words? And actually, we have a result for both that improves, that gives you an answer to both of these questions, and that's what I want to spend the last bit of the talk on. But I'll just state the result. The proof is actually surprisingly dumb and doesn't need any Tauberian. So the problem with the Tauberian theorems, that, I mean, we liked them as in the physics literature for a while, but the problem is that they always take a small region, and they use the behavior in a small region. Like in these simple examples, it was just x going to 1, and it doesn't care about what happens elsewhere. And then it tries to give you some result, and that's just not efficient. We know much more about this partition function than what happens just as beta right approaches 0, right? So you can just go in these proofs of these Tauberian theorems. They're often they're clever estimates on tails of the sum and so on, some big O symbols all over the place. But you can do it yourself, often in a better way, because we know we have much more control of this partition function. So without using any partition functions, we can just write, well, what is this thing we want to know? G plus 2h, phi of h. Or let me first e to the minus beta left h minus b. And then we'll translate that to a phi of h in the same way. We can trade this for a phi of h as long as we know what happens in the right beta left plane, right? Because then we can do the inverse Laplace transform. We can do exactly these manipulations. So I just need to control this guy in the right beta left plane for some j. But what is this? Well, this is just a spin j projection of the partition function. So you can just say, well, it's dz over 2 pi I from minus I pi to I pi e to the zj z, and then the spin j projection is just this beta left minus z and comma z. And to have any meaning, so actually, because this only contains integer spin, I can offset. I can add an arbitrary alpha here. And the choice of alpha does not matter because it has integer spins in it. And then you say, well, this is just the integral of a partition function. I integrate basically, I want beta left in the right half plane, and z basically controls beta right. So I'm just I have to just constrain this by using modular invariance. And of course, the first thing you have to do is probably set alpha to 0 in some way to get some kind of control, some kind of limit where the vacuum in the cross-channel vacuum dominates. So let me just use modular invariant and split out the vacuum in the cross-channel. By I e to the zj vc of beta left minus z vc of z, and then plus some rest that depends on beta left. And that's the non-vacuum. And this thing, right, as z goes to 0, it's the e to the 4 pi squared a over, oops, O over beta right. So in this case, e to the 4 pi squared A over Z. And you see there's now, as Z goes to 0, this thing blows up. Here there's at large J also something subtle going on. So the right choice to pick to get something that looks like what we expect is alpha equals 2 pi square root A over J. So you pick alpha to be that, and that'll at least give you this kind of behavior that you expect, this e to the 4 pi square root AJ, by combining these two terms. And well, actually it turns out that you can vary alpha a little bit around this window. So there's some, you can make, yeah, you can add some gamma here, which is finite in the large J limit, but it doesn't matter. The end result is going to be the same. And then you have picked your alpha as a function of J. There's no more choice. And you just have to make estimates. You want estimates pointwise in the right beta left plane. So you have an integral, and you have an integral of beta right, which goes from minus I pi to plus I pi. And of course, in the middle of this integral, it approaches beta right equals 0, and that's the part where this thing is dominating. But otherwise, you just need to estimate this. And so the way we estimated this was very simple. We used modular invariance a couple of times. Maybe the most important thing to say is that we use modular invariance more than once, right? Here we used it once already, and then we just used it again to bound this thing. And that's something that the Tauberian theorems will never do because they don't work. They work with more general classes of functions. So then you can you can compute. So the strategy is to pick this alpha. You can compute the first thing, part A. And you can bound part B as a function of J and beta left. B, so I mean not the integrand, but the full integral. And that was it. And we just found some estimates that were very, very easy. And we got better results than this whole Tauberian theorem business. So maybe we should, as the physics community, bury the Tauberian ideas and just say, and just try to look also for 4-point functions, look at the functions more directly. And the result we got is, and this will be the last thing I write. So we actually don't need to average over spins anymore. No spins can misbehave. Every spin does the same thing. When you average the test functions, rho j. So this is basically, I mean, it's this A. It's the rho j vac is the contribution from A. So that is asymptotically for very large J, it's the same as what I wrote here. But of course, it has its own corrections and large J corrections and so on. And those are universal and you can just compute them. And then we know that the rest is order J to the minus n for any n, as long as this test function chi of h is infinitely smooth. So that's the thing you can, and we can actually bound these in terms of the value of the partition function. So if you want to get the prediction for spin j equals 20, we can tell you an estimate of this error term in terms of the central charge and the value of the partition function at some special points.
Chi is just a test function.
Chi is test function, compactly support at infinity smooth. So I call it D of R. And actually, so here we see this dense spectrum needs to appear for every spin, right? It cannot be. So this thing that we drew that I had before, that is now excluded because every spin in every finite interval needs to contain at some point an operator. So we see infinitely many operators for every large spin. So infinitely many operators. Well, let me say dense spectrum. And not just in some average. And that's a new result that somehow Cardy could have found, but nobody really bothered to do this. And then we have one more thing I want to say is, so as a consequence, you can say that the average gap is basically 1 over this behavior, right? So you want to say that the average gap between two operators is 1 over e to the 4 pi square root aj over square root 2j. So that's the average density of operators. That's a result that we have now. But, and I'm not going to go into the details, but you can make this thing also, you can make this thing j dependent. Let me add a small j and shrink it as a function of j, so it becomes more and more like a delta function at large j, but not quite a delta function. And the rate of shrinking that we found is that says that the max gap between two operators also has to go to 0. And it has to go to 0 as order small o j to the -1/4. Well, that's almost what we found. We found it as -1/4 plus epsilon for all epsilon beta. That's the best, the fastest shrinking rate that we could find. A faster shrinking rate than that we couldn't prove anything for that. So
sorry, but you're right, little o. So
yeah, the max gap has to be, I mean, for all epsilon greater than 0. I think little o and big O does not really matter.
That's my point. Once you put the epsilon, okay.
No, it cannot be. It has to be positive power here, right? So you cannot say exactly -1/4.
But little o say it's faster than any. So
no, because I think you can do log things and so on. So, right, the powers are not the only thing that exists. So I think it's not
okay.
Yes. So this is what we have right now. This -1/4 seems to be pretty crude. It's due to some very crude estimates of this rest term, this B term. So probably it might be improvable, but I don't really know if it can be improved with just modular invariance. Maybe you need to use more. What else do I want to say? Well, I want to apply the same kind of methods, of course, to the lightcone limit and the 4-point function, the thing you should ask me about. And then finally, I think for people who like chaos, they want the spectrum to look a bit like random matrices. And like I said, you need infinitely many operators in a given window. You need infinitely many operators to do some statistics and see some kind of random matrix behavior. And I think what I want to say with these results is they're kind of green lighting what kind of windows you can sample over to get some random, to perhaps get some random matrix behavior. So we're not saying that the spectrum is random, we're not saying chaos, but we're saying, look, if you average over a window, it should probably not go to 0 faster than this, because then I'm not sure if you can even get do some meaningful statistics. But if you average over a window of this size, then for large spin, you get infinitely many operators. You can do some statistics and see some kind of random matrix behavior. So that's, as far as I can tell, the connection with chaos. That's and the chaotic nature of these theories that people expect. And of course, the real prediction from chaos is somehow has to do with large delta and fixed j, but we're not there exists some estimates that the spectrum has to be integer spaced or smaller, and nothing this refined has been proven in that particular. But that, of course, would be very interesting. I'll shut up. Thank you.
Thank you very much. It's just one quick question, okay?
The general modular transformation. Did you learn anything new or more refined of this formula?
I feel like probably not, but I'm not sure. Of course, there's this paper, yeah, Lawrence and Eberhard and friends said some things about this modular integrals and rewriting them as some over fourth circles and so on. But there's some conjectures in that paper, but that maybe we can prove now for rational theories. But it's not exactly what you're saying, but it's related to more general modular, right? More generally, yeah, there should be an arrow also now backwards, right? We know something about the spectrum. Can you now go back and say something about the partition function in limits that were otherwise under less control? Because now we have more control about the summand, so or the integrands, right? Can you do the integral and make estimates that were not possible before? There's no logical problem with that because the spectral density is positive, but now we know something more. So I think that that's a valid question.
Let's thank the speaker and we postpone the question for the break. Resume at 45, so there is some time.